Okay, so we resume. So the idea with an in-memory grid is that you have backup of data for your, okay. You have backup of data for reliability, and that's done on hard drives. And then for faster operation, you have RAM. Okay, so you have some cluster of hard drives down here. And the basic process okay, so we'll draw an arrow. We've got some back and forth going on there. Okay, we've got hard drives down here. Okay. And then queries and responses. Basically, people asking for data, people getting data back. In RAM, we store the popular data. So, popular data goes here, right? Because RAM is fast, can handle high demand, okay? And handle it quickly. So that's what we want there. But we keep the hard drives. We keep the hard drives down here. Hard drives hold less popular data. They are relatively slow, okay, but also cheap and durable, okay? Non-volatile is specifically what we're looking for here. So, all of the data that's very popular, that people are looking at a lot right now, you keep that in RAM, but you also keep a backup plus backups of whatever's stored in RAM you keep on the hard drives, right? So the popular stuff you keep in RAM to respond to requests. The less popular stuff, like last year's photos that nobody's really looking at, you keep them on hard drives. If somebody asks, yeah, you can serve them up. It's unlikely that you'll have massive demand of 10 million views in an hour for, you know, pictures from my vacation to wherever we went last year, okay? Just not going to happen. So, if you had all the data in RAM, it'd be tremendously expensive. Facebook could literally not afford to store exabytes of data in RAM. They can afford to store exabytes of data on hard drives. But if they tried to store all their data on hard drives, the system would be too slow. They need a lot of extra hard drives just to keep up with demand of popular things. It's much more cost effective, even though RAM is expensive, for things that require a lot of activity. It's much more cost effective to do this kind of RAM setup. Okay. All right. The other thing, volatile memory gets lost when the power goes away. So if you stored all of your memory, all of your data in RAM, you could have some intern trip over an extension cord and boom, there goes the whole system, right? It would be horrible. Hard drives, you know, basically somebody has to set the building on fire. So that's a lot trickier to do, a lot harder to pull off. Okay, so we understand this kind of system? Yes?
What's like an example of like something Facebook would store RAM?
A picture of Kim Kardashian's butt that 10 million people want to look at in an hour, right? Yeah, that was my go-to example last class. Yeah. Okay. So that sort of thing, right? But like, because she might have 10 million people that want to see whatever she's up to. Me, you know, I got a few hundred friends on Facebook, and of those, probably 10% actually are interested in what I post. So at most, I'm looking at like 100 or 200 views of what. I'm not going to have that kind of traffic. My stuff gets stored on hard drives. Yeah. Okay. Now, this leads to the follow-up question. Okay, so I'll mention this just parenthetically. NVRAMs, right, your kind of flash ROMs, these systems are in development, solid-state drives, all that. They're obviously technically feasible. They're just a little bit more expensive. The cost is probably going to go down. But again, at the moment, Facebook has all of these hard disks. That's what they're going to use. They're not going to throw away all their hard disks that work perfectly fine now in favor of an expensive new technology. Okay, so for right now, yeah, hard drives are the way to go. new new capacity that's getting added on may use solid state drives because that'll be a little faster and that'll help out with the system. But for right now, as far as I know, they're still mostly using hard drives for their less popular data. Now, caching. Okay. Caching is a generic computing term for keeping data where it's easy to get to, keeping stuff in general where it's easy to get to. And I gave the example of a garage, right? Tools that you use frequently, you keep them close to the door of the garage, like, your screwdrivers, your wrenches, whatever. If you use it a lot, you keep it where it's easy to get to. Stuff that you maybe don't use very often, like maybe you have electrical things, but you don't use them very often, like, voltmeters, stuff like that. You keep them, tucked away in a drawer somewhere. You know where to get them if you need to, but they don't have to be very easily accessible because maybe you only bring them out once every couple years. All right. So the way this applies to data, there are two basic categories of data, hot and cold. And if you want to, you could specify degrees of hotness or degrees of coldness, but if you look at this kind of simple system here that we've set up, the answer is basically data gets stored in RAM if it's popular, or it gets stored on a hard drive if it isn't, right? And you can still, you can have ranking systems in the hard drives, and some are faster than others, but for what we're talking about, hot data, stuff that you want to cache, you cache it in RAM because RAM is easier to get to, it's super fast. Stuff that's cold, store on hard drives. You know where to find it if you need it, but you don't need to find it right away very often. So that's a prioritization system. So hot data is data that was used often or recently, right? So again, something that there's a lot of demand for, or something that a few people have looked at recently, which is a pretty good precursor to future demand. If people are still looking at it regularly, then it's hot data. If something's cold, right, then it's not. If it's not hot, it's cold. Okay. Now this kind of caching strategy, it applies throughout the computing world, right? Applications and web pages on servers. For example, if you have a website that has many pages like Amazon, you're going to make your most popular products easy to find, right? Those web pages are somehow going to be more accessible than your less popular pages, right? Again, Amazon could store those popular web pages in RAM, the less popular web pages on hard drives. Database tables. You might have some gigantic database with a bunch of different tables. The concept of a table is basically a set of records of the same kind of thing. For example, cars or students or invoices, whatever kind of data you're tracking. A table is a list of all those kind of records of the same kind of thing. Okay? So, if you have one table that's used very often, you probably keep that where it's easy to get to. If you have tables that are not used very often, you don't worry about it. Okay? Likewise, account data for the most active clients. Suppose you're a big operation, you do stuff with investing, whatever, you're a big brokerage operation, big banking operation. You have clients that are very active, you might cache their data in some sense so they get a little bit quicker service on whatever they're trying to do, right? Other clients that are not frequently involved with you, then they get, second tier service. And just as a way of thinking about it, when was the last time you looked at your Facebook pictures from 5 years ago, right? How often do we, I'm going to go through and see what all shit I was doing 5 years ago? Not very often. Now, Facebook has a thing, they'll bring up pictures from the past, like, here's a picture from 2, 3, 7 years ago, whatever. So yeah, you do kind of get a little bit of traffic on those anniversaries, but most of the time, anything you're looking at on Facebook is pretty recent. Okay, so this kind of hybrid database example, this one from Oracle, this is basically what I'm doing. So they have their times 10 product. The idea is, whether it's 10 times faster, 10 times capacity, whatever. Same kind of issue. They decided to call it times 10, 10 times better in some sense. This is basically the same thing that I drew in Paint. Oh, you can't see it because, Paint is screwy. PowerPoint is a little screwy. I gotta X out of this before there you go. No, I don't want to buy it. I just want to look at it. Actually, I could fuck with it. I'd be like, yeah, I'm interested in buying one of your Time 10 systems. I represent the University of Illinois at Chicago. And get them all hopeful, and they'll think, oh man, I'm going to make a big score. I'm going to sell one. No, you're not. Okay. So, data comes in from here, right? This is where the queries and responses are coming in like, hey, Facebook, show me a picture, or I'm trying to upload a picture. Here, this is the RAM, okay? So there's some process that it goes through. You know, these images come in, or they go, say I'm uploading something. Then the question is this going to be popular? Well, probably right away, Facebook is not going to assume it's going to be popular. But certainly, it'll have to get stored in a database somewhere. Okay, so anytime I upload something to Facebook, even if they leave a copy of it in RAM to see what happens, I am certainly going to also have it echoed to a hard drive somewhere so it gets stored reliably. Okay? Now, every now and then, there's going to be this kind of update. So periodically, changes in RAM, right? So if something has become popular, not popular, whatever, this is going to be refreshed. In the case of Facebook, those images get uploaded and they don't get changed. So I don't have to worry about that kind of dynamic control. But some of these that were popular are going to be not popular. They're going to get quietly dropped from RAM. Other ones, right? I might have something that's stored in hard drive, and for some reason it suddenly becomes popular, right? So for example, suppose one of you becomes famous. You write like some kind of hit song, and suddenly a lot of people are looking up all your shit on Facebook as best they can, right? Because they're like, oh, who is this new person? So suddenly, right, something could get pulled out of the hard drives and be like super popular because of some oddball thing like that. It could happen, okay? And then those things, they get pulled and looked into, pulled into RAM. So there's that continuous cycling. Now, if you have a database that's more dynamic, like for example, you're holding bank account information, like, how much money you have after doing various operations, then there can be the need for echoes of new values, right? Changes to the database. The changes happen in RAM, and they get echoed to the hard drive so that everything is kept up to date. But that's a different thing. But same basic idea. You have RAM for your if you need fast operations. For example, you want something in banking to basically be in real time. That makes sense. Or in Facebook, basically you're managing popularity. You want to keep your most popular images in RAM for faster response. But you always need to back them up on hard drives so that you don't actually lose data if something goes wrong. Okay. Okay. So that's the Oracle system. Again, hybrid system with RAM and hard drives, and balance of cost and speed, right? All in RAM would be too expensive. All in hard drives would be too slow. Okay. And when I mentioned this here, backups may be synchronous or asynchronous. Synchronous means the changes to the backups happen immediately. Anytime something happens in RAM, it also changes immediately to one of the hard drives. Some models that can make sense, like again for banking, you usually want all the changes to happen pretty instantly. Asynchronous, right, might be something along the lines of Facebook where, yeah, you have something in RAM, but in theory, there shouldn't really be any changes to it. But if there is, you can do them at batches at some point during the day, right? Once a photo's been uploaded and it's been stored in a hard drive somewhere, you don't really have to worry too much about, constantly keeping everything synchronized. Okay, so synchronous, same time, asynchronous, different times. Okay. Next question, replication. So, replication, general term for, where you store your data, how you manage different copies of data, right? So anytime you have something stored on Facebook, they're going to basically keep a triple copy of it for parity checking reasons. We know if something goes wrong, you need 3 copies in a sense to verify, which one of these is the correct one. You can do that kind of comparison. So Facebook generally wants to keep at least a triple copy. Other reason for that is it allows simultaneous access, right? So if there are multiple people that want to look at something at the same time, even if it's not in RAM, they can still manage, a fairly large number of relatively simultaneous lookups. So, okay. Anyway, so suppose you have a big organization. It has like 10,000 servers and a bunch of different users all around the world. So the question is, should all those servers be in one place or not? Or should you, replicate some of the data to different places? So, let's imagine, for example, again, a very popular image is posted on Facebook, and people from all over the world want to look at it. So one option, okay, so we'll draw a little map here. So what do we have? We have Chicago, we'll do New York, we'll do London, I don't know what else we got. We got, Tokyo, let's do Sydney, and we'll Sydney. And we'll do, I don't know, LA. Okay? So this is our rough map of nodes of the world. Doot, 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 doot. Anybody ever been to Sydney? Yeah? Did you like? What's that? Oh, cool. That was one of the places my wife and I went on our honeymoon. So, did you grow up there? Oh, bummer. Yeah. Well, anyway, it's a fun place if you like parrots, because they have like cockatoos just roaming wild. So you guys know what cockatoos are, right? The big white birds. Anyway, they're just like roving packs of them in the park. It's pretty neat. Anyway, but yeah, I like Sydney. The beer is different, but it's still okay. Yeah. Anyway, so this is some kind of setup, right? So we have all of these different data centers all over the world, and suppose there's an image that's popular with all of them. Well, if I have everything stored in one single location, right? So suppose all data stored in LA data center. What does that mean? Well, number one, all these requests from all around the world, basically those requests have to be routed, right, halfway around the world. That's going to take a little time. The other thing, so delays, bottlenecks, right? If everybody wants to look at something at the same time, this is the only place where it is. I can't really push off that load to other parts of the network. And last, vulnerability, right? Both in terms of, data security, right? If somebody hacks or otherwise attacks this one spot, then the whole system goes down. Also, if there's something like an earthquake or a fire, something like that, that physically fucks up the facilities, then I'm vulnerable to that, okay? So that's the problem. Basically, because of those concerns, you don't want to do it that way. So if all the data got stored in one massive centralized location, first of all, there'd be a distance delay because electrons don't teleport. When you send an email or some other message, somebody on the other side of the world, those electrons have to go through cables to eventually get to where they're going. And they don't get there instantly. The delay is about a millisecond per 100 miles. And you can actually experience this. So back in the day, about 10 years ago, my wife and I got addicted to this one game called Tetris Battle. So you guys have seen Tetris, right? You got the squares and you drop them. Well, Tetris Battle, you basically play against somebody else, and every time you cleared a row, you'd add a row to them. So what you wanted to do was like get a stack where you could get like 8 rows and then finish it off real quick with 2 of those long skinny pieces, and then you'd slam your opponent with like 8 rows at a time. You'd be like, oh shit, I'm done, right? So that was the thing you could do. And as you got better at it, you'd get a higher level ranking, and the system would try to pair you against people with higher levels. Well, the peak level at the time was 25, and what would happen to me is I'd get to 24, and I'd like crush all the level 24 people, and I'd go up to 25, and then I'd play these level 25 people, and they'd smack me back down. And I'd thinking to myself, this is bullshit. I know I'm the fastest, right? But yeah, somehow these guys are beating me. So I thought about it. Well, and I noticed that almost all the level 25 guys had Korean names. And I thought, that's odd. Is there something special about Koreans that makes them unusually twitchy? And I thought, no, they can't. I'm the fastest, right? And I thought about it. I thought, the server for the game must be in South Korea. And in fact, it was. I looked out for it. I verified. Yeah, it was out of Seoul in South Korea. And so, yeah, everything they were doing, they got an extra 1/10 of a second on me. And it was enough, yeah. So I may not look fast, but yeah, when I want to be, I can be. Anyway, so there's that. Actually, side note, so I type reasonably quickly. I'm in like high, double digits, so like close to 100 words a minute, which is fast, but not crazy fast. I actually have an acquaintance with the dude who has like the highest typing speed on record. He got something around like 220 words per second, which is just insane. So, I mean, I say I'm quick, but he's fast. That's insane. Anyway. Other thing, traffic spikes affect all users. So if you have some burst of traffic, right, that's significant, everybody's going to get clogged down with what they're trying to do. Whereas if you have separate data centers around here, well, chances are the surge is going to come from one of these places, not all of them at once, and only that one location will really experience the surge problems. Okay. Availability, it's a little bit trickier to do if you have a big system. I mean, they could manage it. We'll talk about it with Google. I mean, it's manageable, but it's harder to optimize this hot and cold data with more scale, right? If you have a smaller scale operation, and in particular, if you're doing apples to apples kinds of comparisons. So one example, all right, different time zones, right? So people in Facebook, the peak hours are actually early afternoon, but basically the window between like 10 p.m. to like 6 in the morning is pretty quiet on Facebook, right? And they know that. They know that all the people, that are accessing this data center here, they expect that kind of downtime in the middle of the day, right? If they tried to do this kind of hot and cold stuff for all of these times, every part of the world that's active at a different point would suddenly appear to be more active relative to the others, right? So, Tokyo is going to be a few hours behind LA. So when LA is busy, Tokyo might be quiet. When Tokyo is busy, LA might be quiet. If you're just doing comparisons for around LA, then you can say, oh, this content is popular. Even with the downscaling of activity, same data is going to be relatively popular than others. But if you start mixing them up, then you're going to have surges where things of interest to Tokyo are suddenly going to appear more popular, and things of interest to LA are going to suddenly be less popular, and it's going to mess with your ability to correctly classify data as hot and cold. Okay. Last thing, potentially brittle reaction to failure. So if all your data is in one spot and something goes wrong with that one spot, then that's kind of the end right there. Okay. All right, so a solution, of course. These big organizations, they like to decentralize. They like to keep multiple copies of the data different places around the world. And when necessary, you can forward requests to other places. So, give a concrete example of that. Suppose, I'll get rid of those. Okay, so replication. So, let's say information about LA Dodgers probably kept around here, okay? And on the other hand, information in Japanese about local restaurants probably kept here, okay? We can figure, even though baseball is kind of popular in Japan last I checked, stuff about the LA Dodgers is probably going to be overwhelmingly more popular here, especially if it's in English. Likewise, even though there's a fair amount of travel between LA and Tokyo, and there's probably, a number of LA residents who could actually speak and read Japanese, if it's a page that's written in Japanese about a restaurant in Tokyo, chances are there's going to be a lot more demand for it over here than down here, right? So it makes sense. Facebook is going to store data where it's more likely to be used. And this solves the problem, number one, right? Message travel time. So everything's right where you want it. You can do that kind of apples to apples comparisons as far as popularity. And last, if eventually something becomes more popular, you can make a copy of it, right? So if, for example, the Dodgers make the World Series, and there are a lot of people from Tokyo that are considering making a trip out there to watch some of the World Series games, right? You can replicate that LA Dodgers data to Tokyo data center, right? And then it'll be there and you'll kind of solve that problem if it gets popular enough, okay? Similar kind of thing with images. So if I post an image of whatever, I don't know, my kid's first day at school or something, it's probably not going to have a lot of currency outside of Chicago, right? People in Chicago, I got a lot of, most of my friends are in the Chicago area, so that's where it's going to be seen. I have some other people around the world, they might look at it. It's unlikely to become popular enough in any of those places, though, to actually get triggered to being replicated to one of those data centers. Okay. So basically, multiple copies of data, if it's sufficiently popular, can get stored at different server groups around the world, right? If, for example, the LA Dodgers become a really big, exciting thing and people from all over the world are following them, you know, it could also get replicated here, right? Replicated here. There's my, okay? And here, in Chicago even, and New York, and even London, right? It could get replicated to all those places if it's sufficiently popular. But if it's not, Facebook is just going to say, yeah, if there's only occasional traffic asking for it, we can look it up from our server cluster in LA. What else? Yeah. So the advantages, yeah, less latency. It takes less time for the request to go through. Latency just means the delay between making a request and getting the response. Locally important data is more accessible, right? Because, you know, the people have next to them, near them, what they want. And any kind of system failure only affects the local system. So if something goes wrong, if LA, their system catches fire, the rest of Facebook all around the world is still operating just fine. Okay. Now, specific to Facebook, we know a few things. Friendships and activity, they tend to be positively correlated with geographic proximity. That means we're friends with people we live close to, right? That's a pretty good thing. Now, especially in your kind of age bracket, that tends to be less true. Like if you're in high school, then that probably is, you know, very, very true. Most of your Facebook friends are like neighbors or high school people. But then you go off to college, you may be going to college in a different state. You know, others of your friends are going off in different states, right? And then they go off and live their lives wherever. It starts to all break down. But still, you know, I think if we comb through all the data at Facebook, we'd probably find something like 1/2 to 2/3 of people's friends live, you know, pretty close to them. So, with this kind of in-memory grid system, it makes that decision of who is what kind of data is likely to be hot based on, how many of your friends there are in a particular vicinity. So if you post something, if you have like Facebook, last I checked, the count of friends is maxed out at 2,500. If you're not a celebrity, right, if you're an ordinary person, but you have a lot of friends, especially a lot of friends in one area, and you post an image, that might, Facebook might figure, you know what, they post an image, they have a lot of friends, their images tend to get a lot of activity, we're going to keep that in RAM because this person is popular. If you're some sort of celebrity person that has a Facebook page, likewise, you do something, Facebook knows there's going to be a lot of interest in that, that's probably automatically going to get replicated to data centers, near to you. So, in this case example, suppose you're, Taylor Swift. You probably have a worldwide following. You post something from, say she does a concert in Chicago. She posts an image. First it goes to Chicago, but Facebook knows this is going to get some worldwide interest. Boom, it gets replicated to all the data centers. But suppose you're just some, small-scale local band. You might be popular in the Chicago area, but basically unknown in other places. You post something there, even if you have, some kind of Facebook page that's more like a celebrity page, Facebook is going to know, you know what, you don't have that many followers. Most of your followers you do have are around Chicago. We're just going to, put it there in the Chicago data center for now. If you suddenly get a big hit, it goes worldwide, everybody's interested, yeah, it'll get replicated to those other data centers. But for now, just keep it where they think people want it. Okay. Now, we'll introduce the problem of Haystack and what went wrong and how Facebook resolved it. Okay, so Haystack is Facebook's system for storing photos. And this curve here, this is from a few years ago, but what it shows is the percentage of images relative to how old they are. So this is the cumulative percentage. So 100% of their images, these numbers are multiples of 200. So this is 1600, so about 4.5 years. Almost all the pictures that people were looking at, under 4.5 years old. But perhaps surprisingly, about 80% were 1 year old or less. The other 20% were more than a year old. This is what's called a fat tail, right? It's kind of a long, it's less of a fat tail than a long tail. There's a surprising number of photos that are older that are still getting some traction as far as views. What this means Facebook can't set up a system where they basically take 20% of their images and put them in some really slow, kind of system. Instead, they have to maintain pretty good retrieval performance, even for these older ones, okay? Because people are still looking at the older ones now and then. All right. So this one, I believe, I have a bunch of links, articles about how it works, and so a couple of conference papers. But this is the one, finding a needle in a haystack. So this has some good images that are relevant. Okay. So this is how a oh, damn it, once again, you can't see what I'm doing. All right. I'm going to X out of this. Everything okay back there? No spillage? All right. Okay. So this is a pretty good image of what's going on. So somebody's using a browser. The browser goes up to the web server, says, oh, show me this image. Facebook, when that image gets, this person specifies the image that they want. So this is step one. They log on to Facebook. They try to see something, and they see it through a web server that's going to serve up the image. That web server gives them this location of where that image is. So that's the step two coming down. So it says, oh, you're looking for that image. Yeah, you can get that through our content delivery network. Basically, in the case of Facebook, this was another operation that Facebook contracted with that says they're going to manage, all of their popular photos. So if it's stored available through the content delivery network, they'll get delivered back. Otherwise, it might have to get retrieved through photo storage, right? Some set of hard disks up here, and then get pulled back and then delivered through that way. So that's the typical way it happened. There were a bunch of steps involved, okay? You'd find out where it was through the web server, you get permission to see it, it'd get ultimately delivered through Facebook or through a content delivery network. Now, the problem, as Facebook got bigger, this content delivery network had to do more work, and Facebook was basically paying more and more and more every year for that. At some point, they figured out, you know what, we can't keep paying that, but our system as it's set up, we can't operate it fast enough to keep up with demand. So what did they do? Well, the short version is this, okay? Is this. So, now on Facebook, when you go to an image, there's a long URL, basically the internet location of the image. And embedded within that URL for the image is the actual location of where the photo is stored. So back here, right, the web server said, oh, you're looking for such and such photo. There's an ID associated with the photo. It looks up the photo from a database so it can find where it's stored. Okay? Now, the very fact that you've looked at that picture and you have the URL, Facebook knows based from the URL itself where it's stored. So it doesn't have to look it up from a table. It can just parse the URL and figure out the relevant chunk of it and say, oh, this is the URL, so we know it's stored over here. The other thing, even though Facebook still uses a content delivery network for some things, it implemented a faster system. So it has its own separate cache, right, of popular photos. If it doesn't want to run stuff through the content delivery network, it can cache them here and retrieve them faster. So if a lot of people are looking up popular things on Facebook, yeah, it's a quick way to deliver those. Otherwise, it can look them up directly from whatever hard drive they're in. So again, the URL from the image will show, where it's stored here, and then if they look up for the same image here, they can see whether it's in the cache or not, and since that's in RAM, that's basically an instantaneous operation. If not, then they pull it from the Haystack store. So that's part of it. That alone made it faster, that you're skipping the additional lookup step. But the other thing that made it faster is they started having people store photos in albums, right? Once upon a time, if you guys were with Facebook like 10 years ago or so, you loaded up individual photos one at a time, and they could be stored wherever in Facebook's system. But as we know from hard drives, it works faster if you can pull data all from the same track, right? Because then the hard drive spins around and the drive head stays where it is and it just reads as the thing spins. Facebook wants to store photos in that kind of setup because, number one, people tend to look at albums, right? If you go on vacation and you post up 40 pictures of that, somebody who looks at the first picture has a pretty good probability of looking at all 40. So it's much faster for Facebook to just pull all 40 from one continuous stretch on the hard drive rather than have to do the separate seek time to pull each image separately from some different location, possibly on different hard drive disks themselves. Okay? That is, well, that's the gist of it. So, key things, right? Key takeaways. How Haystack made Facebook faster. Number one, less need for looking up where photos are. And related to that, and also metadata like viewing permissions. So metadata is data about data. So one of the things, if somebody tries to click on something on Facebook, Facebook has to know, oh, are you granted permission to even view this content, right? So Facebook doesn't really have to do that anymore because those things, because that info is in the object URL. Okay? Other thing, right? Grouping photos in albums to speed retrieval time because that's how people tend to look at photos. Okay? Now, if everybody mostly only looked at one photo out of an album, then you're not really saving anything, right? You're pulling 20 or 40, however many photos, and somebody's only looking at one. But because a lot of people tend to look at all the photos, it's much faster to do it this way. Okay? So, final result, approximately 3 times faster without any significant new hardware. Okay? That's the real magic of it, is that, you know, it would be easy to say, yeah, we'll buy new machines that are 3 times faster, right? Or we'll upgrade our cable and have 3 times as many hard drives. We could make it work faster that way. But that's a lot of money. Instead, they redesigned their system to basically go a lot faster without it having to really add in any new hardware at all. I mean, they had to add in a new caching system, but at Facebook scale, that's kind of trivial, right? It's not the same as tripling the number of hard drives they have and putting faster cable throughout their system. That's much more expensive. Okay, yes? I can. But bear in mind, you don't have to copy all this I mean, I guess you can copy it all by hand, but it is going to be in the lecture video. But sure, yeah, go ahead. Okay. Does this make sense? Yes. How can you access what? Oh, I have to upload them first. Yeah, I will send the note to the people today so I can get a link to put things on Blackboard. But what I'm going to do in the immediate future, I'll upload them to YouTube. Okay, because YouTube seems to be more convenient for a lot of people anyway. I've had people say that. So, yeah, I'll upload the first 3 of these, and then we'll do the 4th one on Friday. Okay. So that's the gist of Haystack. Okay. And this seems like a good break point. So, any other questions about Haystack? Yes? Yeah, well, all that stuff still existed before, right? All the stuff, there was a photo, you looked it up, Facebook had to consult the database and metadata, so you got permission to view this. So I had to do a couple of lookup procedures, right? And both of those can clear the hard drive seed time, right? So it takes extra time. Now, once you click on something, Facebook knows from the URL of the object itself, knows what the metadata is, knows where the photo is going. So it doesn't have to do those 2 lookups. And on top of that, like I said, the grouping photos and albums makes them delivered in groups faster. Yeah. Yes, vastly faster for, almost no cost. Yeah.
So did Facebook invent the Haystack method, or did they
just designed it in-house.
Oh, they designed it.
Yeah. Yep. Hello. What's that? No labs this week.
Okay.
Yep.
Oh, yeah. So for the RAM and ROM, I'm kind
Okay.
of confused. Like, if I'm a user, there are pictures. Can
Yeah.
I decide which one to save on RAM and which one to save on the hard drive?
No, Facebook
No,
is
right.
going to do that. Facebook is going to say, this one is popular, we're going to keep it in RAM until it's not popular anymore.
All right. So
Yeah.
that one is like not for general use on a laptop, right?
Right.
I mean, yeah. Okay.
But it is true, right? Anything, the same principle applies to your computer. Like if you're running something, I should